So we'll continue discussion on nanofabrication. We talked about uh, how somebody has a design of a chip and how it gets translated. And that's one area or one industry that has pushed uh, nanotechnology in the last 40 years, trying to make chips smaller and smaller, trying to put many transistors together or many components together on one chip. Nanofabrication plays major role in how we build things. There is a distinct difference in building things and synthesizing things. We'll talk when we get forward, when we get into nanomaterials, we'll talk about the difference between nanofabrication and nanosynthesis. The difference is, like we discussed, that you have a design on a mask and you build from larger things to smaller things. But if we use chemistry to build things ourselves, where we add some molecules together and they create something nanoscale, that's another route. So one is called top-down fabrication, the other is called bottom-up fabrication or bottom-up synthesis. Right now we're talking about top-down. So one thing we discussed, we saw, okay, how do you create maybe a PN junction? How do you make a feature? So we saw we could translate feature in silicon dioxide, and here I'm showing is that we have done some steps already. We opened a window in silicon dioxide and we made a P-type doping in an N-type wafer. And now we can cover everything again with photoresist, and we can do another layer of mask alignment. You bring another mask and maybe you want to make electrode connections to that P-type material, like PN junction in a diode, right? So we would put another mask, we would again shine the UV light, and we'll again remove photoresist, remove silicon dioxide, and we can put metal on top. Now we would cover everything with metal. So this red thing is just showing that we can deposit metal over the whole thing. And this thing would be then covering the whole chip surface. And then you can make connection with the outside world. If it's P-type forward bias, you would put positive connection. If it's negative reverse bias, then the same connection can be reversed in polarity, right? You know, forward bias and reverse bias, right? So essentially, we would then cover this whole thing with metal, and then we can make another uh, layer of mask and remove metal at some places. So we have a pointed place where you can make connection. So just a very basic cartoon fundamental idea of how we make devices. Now, this is an example of a device which can help us understand the things of what we call as minimum feature size, the depth of focus, and pitch. Remember, that was three ideas I introduced. How small can we make a thing? Now, in this case, we see that there's, uh, like in previous step, before we put aluminum down, the features are at different height, right? So what is the measurement that deals with things which are at different, uh, if you look at camera, things which are at different focus? What is the property that's involved with that? It's called depth of focus. Did you guys go through the lecture last week? You guys were here with me, right?
Yes, it's one of the things that we talked about in
All
regard
right,
to that.
depth of focus. So this tells us that on the surface of a chip, microchip, there will be always different levels of heights. So when we want to project a design, we want a light to be in focus or reasonably in focus at all those levels. So hence depth of focus comes into play. All right, so again, recapping what we were talking last time, there's one thing called minimum resolvable feature size, or how small can we make a feature? That's the formula for that. And then there's thing called depth of focus. Again, what would be the resolvable tolerance where an image can be considered into focus. So what we want is we want to transfer that design by projecting light. We want that um, many layers to be in focus so the pattern gets transferred. And then there was a plot for depth of focus that for any one specific numerical aperture is a constant which relates to the lens that we use. For any given numerical aperture, if I look at this one plot, I see that when I make the feature size small, my depth of focus also becomes smaller, which means I cannot now focus at different levels. So, and this is real data from a paper. Then another important thing is how close can you make two features next to each other on the surface of a chip? And that quantity is called pitch. How often can you repeat a pattern? So there is a limit to how close you can put them together. And that limit is calculated by uh, this relationship, which is lambda over 2n na. Sorry, up to this point. Here we see that now we are still using lambda. And what is lambda? Somebody remembers what is lambda? Lambda is always wavelength, right? When you use light, the what are fundamental properties of light? One is wavelength. What else? Cecilia, you have the light bulb in your room, right? At your back. So it's white light, right? Wavelength is okay. Here it's combination of bunch of wavelengths, which gives you white light. What else is important about a light source? Dim, dim or bright, right? What do we call that property for a wavelength?
Wouldn't one of the
Okay,
terminologies for how bright something is the lumens that it produces?
right. So now you have to think of it in terms of the wavelength. So wavelength is a wavelength, like it's going like this. A wave is going like this. Wavelength tells us how often does it repeat. The other thing is amplitude, which tells you how bright the light is, right? So the other thing is amplitude. But here we are concerned with the wavelength right now. We'll talk about uh, intensity or the amplitude later on. So when you have these features in front of you, then we see that whatever light we use, wavelength is going to be the most important factor in deciding how we do nanofabrication, how we make small things. Now, if you if you want to make things smaller, you can just keep on making lambda smaller and smaller, right? You can just keep on making wavelengths smaller and smaller. And this is what they did. If you, for this data shows from 75, and you can see that coming from 75, the wavelengths started 405 nanometer, 436, 365, and then we are at 248 and 30 nanometer, right? So we can keep on pushing the wavelength down, and this can keep on making our feature size smaller. But there is a problem with this whole thing, because when you, for every light source, there is a relationship with how much energy you can transmit or how much energy it carries with it. And that fundamental relationship is hc over lambda. Energy can be found for a wave from this relationship where c is speed of light, h is a thing called Planck's constant. If you have taken solid state devices or electronics course, you would have known Planck's constant, right? Which is a number. Now these two are constant, so we can find a number which is 1.24 electron volt. So H is, sorry, E, energy of any wave is inversely proportional to its wavelength. If you make wavelength smaller and smaller, what is happening to energy? Yes, can you hear me? So there's an
Yes,
inverse.
I'm sorry. It's just that I was looking to make sure the what the variable h was because I wanted to make sure I was caught up. I didn't quite catch that last question.
H is Planck's constant. So it's just a constant. What I'm saying is, if you make lambda smaller and smaller, what will happen to energy?
Wouldn't it get bigger?
It gets bigger and bigger, right? Yeah. So that's a simple relationship. 1 over E is equal to hc over lambda, or E inversely proportional to lambda. Now, on previous slide, I was saying that one way to make things smaller and smaller is that we can make the wavelength smaller and smaller, right? Which we see the trend here. But if you do that, the energy of the waves becomes too large. It becomes too large that the optics or lenses, like we have lenses in our glasses, it starts messing up with the lenses. It starts making the lenses thicker or dense. So it says here higher energy is a problem because it starts having issues with the optics materials. Remember, we are talking about optical lithography. We are talking about using light to and using lenses to focus the light and to do lithography. So shorter wavelengths is good to make things smaller, but then the problem is that we start getting into energy troubles. So this is, we can find out from these wavelengths, you can get these kind of feature sizes, but then we have to know that this is not possible because the energy of glass, which is quartz, it almost starts approaching that energy. So what is the energy? If you, okay, who has taken solid state devices course? No one. All right. So materials, all materials, especially semiconductor materials, they have a thing called band gap. So there are electrons which are in valence band, and you and those are not available for conductivity. You have to provide energy, so they have to jump over a band gap and then they go into conduction band. Just a basic theory that electrons are not available for conductivity unless you supply some voltage and make them available for conductivity. It's like you have to provide 0.7 volt for your diode to start operating, right? So you have to pump some basic energy before they become available for conductivity. Now, quartz glass is an insulator, but it still has a band gap. If we push too high of a wavelength, that energy is almost close to the wavelength of that glass, which means there are few things happen. It densifies the optical material, it causes defects in material, silica is also glass. The transmittance goes down, right? So now which means the light cannot even go through. So we have to find other solutions to deal with that situation. So hence, it's not always possible to keep on pushing the wavelength to have smaller features. So it's not always possible that you can push the wavelength down and make smaller features and have good depth of focus, and you can make many things smaller and smaller and close to each other. The three criteria you have to remember: minimum feature size, depth of focus, and pitch, which define of how much density can we pack in a chip, for example. All right, so if we keep on looking at how they did, they kept on, then they started using F2 laser, right? F2, what is F2? What is F? Fluoride, right? Laser. But it has so much energy that you cannot use glass. So you have to, instead of having a glass lens through which the light goes through, now we want to use what we call reflective and refractive optics. So light you want to strike to the surface and push to maybe focus it and to get the same projection thing done. So with this, they pushed it down to 150 to 200 nanometer, and this is called deep UV.
Would this be essentially fiber optic, like the fiber optic cable?
So if you think about it, fiber optic is also something where the light travels by reflecting to the walls of the fiber optic, right? So light keeps on reflecting inside the fiber optic. So that coating of the fiber optic is what makes that happen. So it's a similar idea that reflective lenses would be used to narrow down or to focus the light source, the light that's coming.
Okay, I was just asking to get a better visualization. I know it's a lot smaller, but kind of something in
Right.
mind.
So the idea is that you still have a kind of a microscope, cylindrical uh, equipment, but the light source has to now, instead of using lenses where the light goes through and focuses, you have to use what you call reflective lenses, and you have to adjust reflective lenses to focus the light. Right. So then there are other kind of sources, light sources that have been used, but they all have had problems. Either the reflective, uh, either the lenses were very expensive, or the transmitters got reduced. So these are few light sources that have been used to make those. And as of now, the optical lithography, it's not as of now, but 10 years ago, they could make 100 nanometer with deep UV. But 15 years ago, they could use 100 nanometer by using just deep UV, right? In that wavelength. And that's what gave us those devices which had minimum feature size up to 50 nanometer. Now, industry is at 4 nanometer. So you can make things 4 nanometer size scale. Now, this has become enabled by what is called next generation lithography. We will talk about next generation lithography in the next module. We are still in the second module. I think last time I said we are in third module, but we'll talk about, it says NGL, next generation lithography. We'll talk about this in the next module. Today, I just wanted to talk about uh, nanofabrication and how we have been making things smaller and smaller with optical lithography. So there's another thing they did with lithography, that instead of using air as the medium, they put water between that lens and the wafer. Sorry, between the, so you have light source, you have a lens, you have mask, then you have lens. So instead of using air, they have started using very pure water without any particles or anything, pure water. So now we can play with refractive index, and that gives us smaller feature size. Another trick, there just two, three tricks we'll talk about, and then we'll stop on this. Another trick they've done is that they have started changing masks by adding extra features. So now when you have very small feature and you put light, if it would be the same way, you would not get the feature all the way. So they have putting like hammerhead type of features on the whatever needs to be made, and this way they can make exactly the features they like. There's something written here that a mask set for any chip costs about $2 million. So that's the thing, that you cannot change those masks so often as well. So whatever technology level we work with, whatever light source we work with, then we have to stick to it for some time. And one mask set is good for 2,000 to 3,000 wafers, right? So again, another trick they have done is, instead of just using glass and a transmission mask, they have put some material that can phase shift the light. When you have a wave traveling, it's always traveling with some phase. If there's another light which is out of phase, and if they come together, they would cancel each other out, right? Constructive and destructive interference for waves. So they have used a phase shift mask where now when the two waves come together, instead of aiding each other and making too much energy, they cancel each other out. So you get a very clean feature made on the surface of your wafer. So these are called phase shift mask, PSM. So there are two types, alternating PSM, attenuated PSM. So I just want to share two, three tricks that have been done to keep on pushing the size of the chip features, so we can keep on making smaller and smaller things. So now, to recap, we have been able to use lithography, optical lithography, to make things smaller, repeatable, and cheap. And this has enabled the high volume manufacturing in the semiconductor industry by changing the light sources, by keep on pushing the wavelengths down, and by making the resolution of the optical lithography good enough so we can make those uh, all the components on the surface of the chip. And then we get into what you call next generation lithography, where we use either X-rays or we use other types of light sources. These are not light sources. These are sources of particles, for example, electron beam. So we, instead of using light in wave, we use the actual electrons and we bombard those electrons to make small things, right?
So,
Yeah, question.
I was just saying, so essentially move from light to radiation.
So we, now radiation, when you say radiation is again waves, right? So that's X-rays, right? But then X-rays have its own issues. You cannot make mask good enough for X-rays because X-rays can pass through everything, right? So the mask has to have a material which is opaque to that light source that we use, so we can make the feature in that to put on the chip surface. But that's where we have different challenges there. So you may have to make a mask made out of metal instead of just glass. But that's something we'll discuss in what we call as next generation lithography. So if you recap, we have been pushing down the UV, and we have, at best, we got a 30 to 70 nanometer with UV lithography or optical lithography, and it has its own challenges. That optics go bad because the band gap of the light starts messing with that. And wavelength is not the only solution how you can make things smaller, because when they become too small, they start messing with the lens material itself. So we have to then uh, get to other ways. Now, there is a plot, it's called Tennant's Law. It was a paper published in 2003. So from there, we call it Tennant Law. What it says is, if you look at this plot, now the y-axis is resolution, x-axis is areal throughput. What do you mean by areal throughput? So when you have a wafer, you have to shine light, right? Expose it, and then it has to go, another one has to come in. How quickly can we do the process? That's the throughput. Or even if you have a large wafer, you just expose one part, then you go to another part, you keep on exposing the whole. Remember I showed you the wafers? And I showed you on a wafer, there were small dies. So if the wafer is too big, you cannot expose the whole thing together. You have to expose smaller pieces at a time. That means the throughput becomes slow. Throughput becomes slow, which means it takes more time to process X number of wafers, right? So areal means how much area can you process in 1 hour, for example. So if you make the feature size smaller and smaller, throughput also goes smaller. Is that good or bad for the business?
Bad.
It's bad, right? Now we have to spend more time in making the same chips. And this is essentially what has happened. So if you look at the plot, it's showing a straight line that you were using optical step and repeat, and we kept on introducing newer and technology to make things smaller. But what it means is that we are getting slow down in making those chips. So this way, when you go down, so there's all different technology, FM. We haven't, we will read this side in the next module. But you have to see the trend. We are going in this direction. We can make things smaller, but the throughput goes bad. So basically, if I just put the trade-off is simple. The trade-off is that when I make dimensions small, my throughput goes high. Ideally, I want to be on the right-hand lower side, right? What does it mean if I'm on the right-hand lower side? Hector, what does it mean to be on the right, on this plot, to be on the right side lower corner? Hector, can you hear me? We cannot hear you. Yeah, Edgar, go ahead.
Being on the right side would mean that you have much larger throughput, meaning you could essentially make more at the same time. Yeah, being at the lower end means you have much, I don't know whether to call it higher resolution, but essentially more precision.
So resolution is basically minimum feature size.
Mm-hmm.
So you can make smaller features while you can maintain high throughput. That's the goal. That's the wish list. That's the wish list. This is what it says then. We want to move away from the line towards the bottom right-hand corner. But that requires major investment in tooling and process. When one mask set is in millions of dollars and you have to change the whole machinery, that's going to be many, many, many more millions of dollars. Think about it. Right? So that's something which has led us to what we call as next generation lithography. But we have defined some metrics. We want high throughput, we want smaller resolution. You have to have high quality, which means you want to reduce the defects so our yield can be higher. There's always some wastage, right? Whenever you make some chip, there's always some wastage. Whenever you buy, now it's getting less and less. When you buy a computer thing, yeah, they have warranties because they know things can go bad. They replace it. That's what you mean by quality, yield, and defects. Number 4 is investment. Investment in equipment, in machines, and investment in training the people as well. investment in getting people trained enough so they can start making those chips. So that's a huge investment. Now, when you make things smaller, we want to do things automated. So you don't have to get the errors out physically by yourself. But when you make things small, we are reaching the physical limits of things. We are reaching up to the atomic scale of things. That's bringing its own challenges. And alignment is related to that if you make one layer, then when you come back to make another layer, if they're too small, it's very hard to align with the what the feature was made before. So there are lots of questions, lots of challenges with optical lithography. Questions? All right. So in lithography, we are making things from, we are using mask and we are making larger things. From larger design, we are trying to make smaller and smaller things. We call that top-down approach. Nanomaterials. Nanomaterials is mostly when we do reactions and we do what is called bottom-up synthesis. So you, in nanomaterials, most of the nanomaterials, we start from basic chemicals, we do controlled reaction, and we build some nanoscale features or nanoscale things. There are definitions, like there is definitions for nanotechnology. We call a cluster is where we get about 50 units of atoms or molecules together, and we call it a cluster. If we have a bunch of nanoparticles, which are in the size of 1 to 1000 nanometer range, and you mix it in solution. The thing in solution is when when we mix sugar into water, right? Well, lots of sugar gets mixed. What happens to some of the sugar particles?
Oversaturation, and they don't actually blend within the molecules.
They settle down, right? They settle down at the bottom of your cup, your glass. Why do they settle down? Gravity, right? So gravity acts on them and it settles up. Now, what if I tell you that if you grind those uh, crystals or those particles too small, that gravity does not affect on them? They would stay suspended forever. They would never settle down. So that solution is called a colloidal solution. The second word, collides. So these are particles which are in the range of 1 to 1000 nanometer, and they would be stable in liquid phase. What I mean, stable in liquid phase, they would not get dissolved like sugar, and they would not settle down like sugar again. Yeah, yeah. Question.
That would
So
be like salt then?
Salt, but salt get dissolved.
that brings up the question. Then it might be particular to this atom, but I'm oversimplified. Back when I was in chemistry class, I was told that essentially, like whether salt or sugar, essentially, sorry, I let go of the button. But essentially, you know how the water molecules, like the big oxygen and the two hydrogens on the side, that the way that it dissolves is that it essentially fits in between those two. Uh, so when you bring that up, uh, when it gets to that small of a level, regardless of whether it's um, whether it's organic particles or nanomaterials, anything, at then that point, the universal theory of gravity, as in the formula that we learned back in physics, be applied to each individual
No,
structure at that level?
no, that's a different example. The sugar or salt, when it gets dissolved, that's not a colloidal solution. That's a totally, that's where the ionic forces come into play and sodium ions and chloride ions separate out and they get dissolved. We are talking about things that would not dissolve at all. They would stay suspended in liquid, they would stay stable, they will maintain who they are, and they would never settle down. This is okay. I started with the sugar example, but the only thing pertaining to the example was settling down. That the bigger grains, if you take bigger, what do you call the raw sugar, bigger grains, it takes more for us to shake it to get it dissolved, right? But it gets dissolved eventually. But particles settle down because they're too big to stay suspended. Now here what we are talking about, the material, and these can be solids, these can be metallic particles, but they're ground so small, they are in range of 1 to 1000 nanometer, they would never get dissolved in water, for example, and they would never settle down because the gravity has no effect on them. So they are stable. So we call those things colloids who stay stable in liquid phase, and their particle size is 1 to 1000 nanometer. And the third types are what we call nanoparticles. These are again very small particles of solid. It can be iron, it can be, I don't know, anything you pick, aluminum, titanium. They're so small in the range of 1 to 100 nanometer. They can be crystalline. Maybe you can grind silicon into that small size scale. They can be just aggregate of small crystals, or they can be, they may be just no crystal in it, like iron. And then we say, okay, nanocrystals, when we are talking about a big crystal like diamond, but ground into smaller pieces, right? So very small, distinct differences, but nevertheless, we need to know when we hear the word, we can understand what does it mean if you know the basic definition, right? So these can be organic, carbon-based, or it can be non-organic, metals for that matter. But the organic compounds have their special class now in nanomaterials. And some of you have seen that already, graphene, for example, or nanotubes, carbon nanotubes. We'll talk about them also. Now, they can be, again, nanomaterials divided or categorized in different ways. We can have what you call just one type of material in that thing, which is, let's say, one phase or multi-phase, 1A, 1B, very small amount. So it can be particles which have chunk of one type and then chunk of another type, then chunk of one type. These are on the surface. And in the particle shape, they can be either coated on a surface, maybe suspended in solution, maybe thoroughly mixed in a solid. It can be just airborne. Now, when you talk about airborne, why do we wear masks? Dan, why do we wear masks?
To catch the microparticles
To
that we breathe.
protect your face from either the air particle or liquid particles that
How,
our spit has.
how small are those particles?
That's why it depends on the grade. That's exactly why hospitals have N95, because that one's been proven to catch small enough particles. But for general public, especially with a mass shortage, it's just a general cloth because we're still supposed to be maintaining 6 feet apart.
So how small are those particles?
Yeah, I forgot the number, but I remember I remember that the reason why we use this mass is because of the three filter composition is to stop a specific size of particle, but it's one that it's what was it, like as small as a particle of what? I forgot the size, but like I remember.
Okay. So what is the size of uh, coronavirus?
I just looked it up and it said 5 micrometers in length.
That's a droplet. That's the droplet, right? What is the size of the coronavirus itself?
In nano?
Yeah. How many nanos? 70 to 90 nanometer. Now, it is a nanomaterial. It is a nanomaterial, and especially when it may not survive in air, but when I'm throwing out liquid, it has liquid protective layer on it of my saliva, and it stays suspended in the air because it's so small, the gravity does not affect it. That's why it stays airbound. Have you ever thought why does it stay airbound? Why doesn't it fall down and get to the floor? So instead of having air filter, we should be mopping our floors. But that's the reason. It's a nanomaterial. Gravity does not have effect on it. What's the general cutoff of gravity effect on particle size? 3 to 5 micrometer. Something smaller than 5 micrometer generally is not big enough to feel the effect of gravity. Hence, it stays airborne for a long period of time until the water dries off and it just gets destroyed because of the air. It doesn't have a medium to thrive on, right? But anyway, so there are ways how we, uh, different ways how we categorize them.
So do you have a question?
Yeah.
What does it say that COVID is around 60 to 140 nanometers? Like, why is there a range? What determines the range that it can be
Right.
60 or 140?
Yeah. So how do we look at these things? Is a it's a cap it's a small ball, right, which carries the RNA in it. Now, the material itself, the composition of its body, there are 4 or 5 subcomponents which make the whole thing together. And each thing has smaller variations into it. So, which causes the overall size to have a range instead of an exact number. And in solution, as human, we live in air, right? So we don't see liquidy things. Liquidy things always have a very slushy kind of a boundary. If you go underwater, you see, look at fish. Fish has very soft body. Things which are suspended in liquid, a lot of time they have a very soft boundary to it, not like solids like we see that. So these things live inside, hence they have a range of the size that you can look at instead of exact size. Right? All right, so now this is a very interesting figure. Yeah, colors, yeah, we have done false colors on this. Actually, they all would be electron microscope pictures. But the thing is, it's all one material. It's zinc oxide, ZNO. But by changing the synthesis conditions, by changing the atmosphere, by changing the other gases in that chamber, you can synthesize many different forms and shapes of the same material. Same zinc oxide, but nanoscale, you can taper, change, direct its growth in so many fantastic ways. So people have whole career around nanomaterial synthesis. You can look up the Dr. Z. L. Wang, Georgia Tech, you'll be amazed. Just same material and how many different ways they have grown this. So nanomaterials can be growth in all forms and shapes. And again, there are top-down ways how we make them. We can start with bigger material and chisel away. Chiseling is done by etching. We talked about that. By etching away extra material and getting to that smaller amount, we call it top down. Or we can start bottom up, where we can put atoms together, we can design them to behave in a certain way, and we can create nanoparticles out of those. So nanomaterials can be either hard, they can be also soft materials, right? Polymers, plastics, what we call, but polymers is a little bit more uh, generic term. And if you look at the types, classifications, characterizations, uh, or their methods of the fabrication, there is a whole range of those things. We have carbon nanotubes, which are made of carbon. We'll look at those in another, I think I'll put up a micro lecture on that. There are dendrimers, which are branched particles. You look up each name and you'll find fantastic examples of how we make these things so small and we control their features and we control their shapes. There are liposomes, which is uh, another kind of a long circulatory things. And these, many of these come from living systems inside the body. They exist and they are built up by living systems to do many different things. There are metallic nanoparticles. All right, again, you can either start with bigger things, grind them, chisel away, and come up with them, or you can create from very fundamental crystals. There is nanocrystal quantum dots. It's a special class of nanomaterials because they have optical properties. They give light. They absorb light and they give light. Quantum dots has a special role when we talk about bio applications. We'll talk about that also. So, and then there's another thing called micelles, polymeric micelles, and they are also what you call entrapments. They can have layers and layers of chemicals in it made of polymers. Polymeric nanoparticles. These are where you can make these things out of long chains of atoms. And they are softer than, of course, they're softer than metallic nanoparticles. So these are few examples. Now you can look at those things closely and we can see many applications, especially when we are talking about KPR